Definition: a function that is continuous on all the real line, which means to all values of x's between negative infinity and infinity, is called continuous everywhere. The functions that we know are continuous on their domain. For example, polynomial, exponential and logarithmic functions, odd and even root functions, rational functions, trigonometric functions, and their inverses. So here are the functions that are continuous everywhere, and their domain is also the set of all real numbers. Polynomials, exponential function, odd root functions, and the cosine and the sine functions. Example: the domain of the function x plus 3 over x minus 3 is everything except x equals 3. This function is continuous on all the real line except that it's not continuous only at x equals 3. So it is continuous on its domain. Properties of continuous functions. So here is the theorem. Assume that f and g are continuous at x equals c. Then all these functions are also continuous at x equals c. K times f, when k is any constant, the sum of the functions f plus g, the difference f minus g, the product f times g, and the quotient f over g, provided obviously that g of c is not 0. For example, if you look at this function fx, it is continuous everywhere, because it's made of a sum and a product of functions which are continuous everywhere. So as long as there is no quotient, you don't have to worry. If you have a combination of addition, difference, or product, or multiplying by a constant of functions which are continuous everywhere, the new function is going also to be continuous everywhere. Example, here is f and g. Now let's see what happens to the quotient. We know that each one of them is continuous everywhere because f and g are just polynomials. So even though the sum and the difference and the product are continuous everywhere, but if you look at the ratio of f of g, then because g of x is 0, where x equals 3, we get that f over g is discontinuous at x equals 3. Theorem: assume that g is continuous at c and f is continuous at g of c. Then the function f composed with g of x or f of g of x is continuous at x equals c. Any function that is a result of combination of functions that are continuous everywhere, including now we can see composition, is also continuous everywhere, except that there is a ratio and the denominator is 0. For example, look at this complicated function. Well, if you really notice, this is a combination of functions that are continuous everywhere. And there's no ratio here, so I can conclude that this function is continuous everywhere. As a result, for any number c, if I would like to take the limit of this function when x approaches c, this is just f of c. Which means I can just substitute c instead of the x. So even though this is such a complicated function, we can easily find the limit of this function when x approaches 0. So I'm going to substitute 0 for x. And this is what I get. Please recall, cosine of 0 is 1. Theorem: assume that g is continuous at c and fx continuous at g of c. Then the limit of f of g of x approaches c equals to f of the limit of gx when x approaches c. Example: here is a function that is a composition of two continuous everywhere functions. One is a polynomial and the other one is cosine x. So we know that the function f of x is also continuous everywhere. Because it is continuous everywhere, then I can evaluate easily the limit of the function wherever I want. For example, where x approaches -1, I can just actually use the theorem and say that I can switch between the cosine function and the limit. So this is cosine of the limit of x approaches -1 of x to the power of 2 minus 5x minus 6. And I get cosine of 0, which is just 1. But I would like to recall also that because this is a continuous function, then I know that the limit of the function x approaches to -1 is f of -1. So I can just substitute -1 for x, and I'm going to get that. Removable continuity. Let's observe the graph of this function. It is a line with a missing point. The missing point is 2, 4, because x equals 2 is not in the domain of the function. fx is continuous everywhere except at the point where x equals 2. Let's take the limit of the function where x equals 2. Reduce cancellation and we get 4. Because there is only a hole in the graph, we can fill it by defining a new function that is continuous also at x equals 2. So it's going to be continuous everywhere. This function is going to fill in the hole. So here's the new function capital F of x. When x is not 2, it's exactly the old function. When x equals 2, we are going to define the new function as 4 because it's the limit of the function when x approaches to 2. The new function is continuous everywhere, we can check. If you take the limit of the new function when x approaches to 2, you get 4, which is also f of 2. So by the definition of continuous function, it is continuous at x equals 2. And when x is not 2, it's obviously continuous. Assume that f is continuous function on the interval ab, except for one value x equals c on the interval ab. If f has a limit at x equals c, then the new function that is defined as capital F of x equals, when x is not c, it's the old function f of x. When x equals c, the value of the function, the new function, is the limit of the old function when x approaches to c, and this function is continuous for any value on ab. You can check that because the limit of the new function x approaches to c is really equals to capital F of c. If a function does not have a limit at x equals c, then we can never remove this problem. There will be no way to fill in the point. For example, this function gx does not have a limit at x equals 0. So it will be impossible to fill the point where x equals 0, which means there is no way to remove the problem, and there is no way to fix this one to be continuous at x equals 0. This piecewise function is made of two pieces that each one of them is continuous as a polynomial. But let's see what happens at x equals 7. It does not have a limit. Because there is no limit, there is no way to fix this one to be continuous. There is actually a pretty big jump. So if it's more than just filling a point, it is impossible to remove this discontinuity, and it's going to be forever discontinuous at that point. I would like to show you the graph of this function so you can really see that. here is this branch, and here's the other branch. And there's a huge gap that cannot be just bridged by filling one little point in.